Welcome to Pre-Calculus. Today we will investigate function symmetry, focusing on how to prove that a given function is even, odd, or neither. Let's take a look at a total of 4 examples. We'll start with 2 examples. Let's head over to our notes screen. The first function we want to take a look at is f of x equals x to the power of 6. So our first task is to graph the function by creating a table of coordinate points. And we'll start that by making our table. Let's grab a pen here and record our table. And recall that with the table, here I need to zoom up to the correct one. Let's find the correct one. So there we are. With the table, we'll place our x values in that left column. And we're going to evaluate f of x. Remember, that's the y column. It's the values that depend on the x values. So for our domain, let's choose -2 through +2. And we choose those 5 because they are centered around the origin. So -2 through +2. And at that point, I want to evaluate the y values by plugging these x values into the function. So my first value is -2 for x. So I'm going to calculate f at -2. So I'm going to be careful to put that in parentheses. So it's -2 in parentheses to the power of 6. And then I'm going to expand that. So within the parentheses, I'm going to write -2 times -2 6 times. -2 times -2 times -2 times -2. So the power function x to the power of 6 literally means take that x value, multiply it times itself 6 times in this case. I'm going to pair these up just to see what's going to happen to the sign. Is this going to give me a negative number or a positive number? So -2 times -2 is +4. And I've got 3 pairs of those, but at that point I see that 4 and 4 and 4, all of those are positive because I've paired up the negative pairs. So all I need to multiply is 4 times 4 is 16, times 4 is 64. And that gives us our first coordinate point, -2, 64. We'll keep going. Let's evaluate f at -1. So again, I'm going to use the parentheses, place the -1 in the parentheses, raised to the power of 6, and expand it out. That's -1 times -1 times -1 times -1 times -1 times -1. So 6 of those. And just like we did with our -2 values, I'm going to pair them up just to simplify the multiplying. So each of those pairs, -1 times -1 is +1. And then 1 times 1 times 1 is simply +1. So we'll record that -1, +1. Now we're going to calculate f at 0. This is going to be very easy. Again, the function says multiply that 0 times itself 6 times. So we've written it 0 times 0 times 0 times 0 times 0 times 0, which is 0. In fact, we'd only need one of those zeros in a product to multiply to 0. We've got 6 of them. So that is the point 0, 0, or the origin. Our next value is +1. So again, I'm going to put it in the parentheses, but note with the positive integers, we don't really have to mind the sign so much. We know they're all positive, so the product is going to be positive. 1 times 1 times 1 times 1 times 1 times 1, well, that's 1. And that would give us the point 1, 1. I'm going to note that in the y values, I have a symmetry forming. So as we start to think about even or odd symmetry, some of what we can see in the table will help us to decide that. When x is -1, it yields a y value of 1. When x is +1, it yields a y value of 1. Well, let's see if that pattern works with f at positive 2. Is that somehow related to f at negative 2? Let's see. Again, in parentheses, 2 to the power of 6, which is 2 times 2 times 2 times 2 times 2 times 2. And again, I don't need to mind the sign so much, and I know that 2 times 2 is 4. Pair these up. I got 3 products of 4. 4 times 4 is 16, times that third 4 is 64. And that does show the same type symmetry we saw with the -1 and the +1. Positive 2 has the output of 64. So does -2. And again, in a moment, we'll use that same idea when we go to say, is this an even or an odd symmetry function? First, though, we should graph. So when I go to graph -264, that's off the screen. In fact, it's up above the room. So I'm going to just understand that I've got -264 in my table. I can't really represent it well on the graph. I can graph the next point, -1, 1, however. 0, 0's there, 1, 1's there. But again, at +2, 64 is off the graph. Well, we'll sketch that function. So just to indicate that this function's very high in the sky at -2, I'm going to start a little to the right of -2 and descend down. And then also as I head up, I don't reach +2 by 8. In fact, I have to get to 64. So there we've got a nice graph of our function, x to the power of 6. So at this point, I want to make a hypothesis to whether I believe this function to be an even or an odd function, or neither. And we're going to do that based on the graph. So just to give a visual, what I've sketched is x squared. So this is our traditional example for an even function. And how we know an even function is that it is reflectional. What we should see is that this side of the graph, if I were to fold it over the y-axis, it should land exactly on the other side. And in fact, with paper, we can kind of demonstrate that. If I fold this over, this one side of that parabola would exactly hit on the other side. So that's even symmetry. It's a reflection over the y-axis. That's in comparison to an odd function, which is not reflectional, but rotational. An odd function is a rotation. And when we say rotation, what we're claiming is that if I rotate this graph 180 degrees, so it's kind of a half turn, if I get back to the same graph, so notice when I started, I had part of this graph here in quadrant 1, part of it down here in quadrant 3. If I rotate it 180 degrees around the origin and get back to the same graph, so notice it's the same this way as it is rotated 180 around the origin, we would say that that function is odd. So we can make a hypothesis about the function symmetry just geometrically. So looking at our graph here, f at x equals x to the power of 6, my observation is that if I folded this graph across the y-axis, this right-hand side would exactly land on the left-hand side. So my initial feeling is that that would correspond with my even symmetry or my reflectional symmetry. So I'm going to make a claim. I believe that this is even symmetry. Now, once I make that hypothesis, I need to prove it. So we've got the rule for even symmetry here. And it's an algebraic statement that if I've got f at -x equals f at +x. Now, if that is true, algebraically, that would prove that this function is an even symmetry function. Well, let's see how that works. So what I'm going to do is I'm going to pick up the rule for our function, which is f at x equals x to the power of 6. And what I want to do is use that function just to calculate what would f at negative x be. So just like we had done with our coordinate points with our x values in the table, I'm going to put parentheses and I'm going to put negative x, since that's what's here on the inside of the function notation, raise it to the power of 6. Well, let's expand that. So again, negative x to the power of 6 is negative x times 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 negative x, just like we had done when we were evaluating with -2 and -1 in our table. Again, I'm going to pair them up just as we had done in the table to resolve the signs. So negative x times negative x is positive x squared for each of these pairings. And then x squared times x squared is x to the power of 4. X to the power of 4 times this last x to the power of 2 is x to the power of 6. So what we see is through this kind of long multiple step equation is that when I plug in a negative x, it still gives me x to the power of 6. Well, let's investigate that other side. So we had said, okay, I need to think about if I put a negative x within the function, the right side of the statement is simply f at x, the rule without any change. So I'm just going to bring it, again, I'm looking back to the rule that we had originally. F at positive x is simply x to the power of 6. Now, what I want to do is I want to compare these two evaluations. What do I get when I plug in negative x? What do I get in when I just use the original function f of x? Well, x to the power of 6 and x to the power of 6 are identical. So what I can do is trace back all the way to the left and make the logical claim that those two that we started with are also equal. We can claim f at negative x equals f at positive x, which is a rule that says, and by the way, that 3 dots means therefore, this is even. And this statement down below, I'm going to box the whole statement, is our proof algebraically that this function is even. So definitely as you're doing your work, you want to graph the function, make the claim, and then show this algebraic setup to say, hey, my hypothesis is provable using that rule either for even function or odd function. Let's take a look at one more example. So here we've got the function f of x equals x to the power of 3. We'll set up to graph the function first, so x, f of x, and we'll choose again our traditional 5 values, -2 through +2, and we'll jump right into the graphing. So f at -2 is, again, I'm going to use parentheses carefully because I got to deal with that negative sign, to the power of 3. And just like we had done previously, I'm going to multiply those out. So that's -3 times -3 times -3. So I'm going to multiply one pair of them. -3 times -3 is +9. But notice the third one does not have a pair to go with, so it's just -3. 9 times -3 is -27. So we'll record that point. I'm using the wrong x value. Let's get back to where we should be. I'm going to back up. I used 3 instead of 2. I'm not quite sure why, but you know, things happen. So I'm going to fix that. -2 becomes our value underneath the radical. So we paired two -2s. -2 times -2 is 4. We do see the same pattern though. 4 times -2 is -8. And I believe that fixes the glitch. So we got the point -2, -8. All right, let's keep going. F at -1 is in parentheses -1 to the power of 3, or -1 cubed. Expanded out, that's -1 times -1 times -1. And I'm going to pair two of them. -1 times -1 is +1 times the spare -1 yields the -1. So notice this stuff is staying negative. That'll tell us something in a moment about its symmetry. So -1, -1. Pick up with f at 0 is 0 to the power of 3, which is 0 times 0 times 0. And just as we've seen with 0 to the power of 6, we only need one of those zeros in the product to give us a result of 0. We have the point 0, 0 at the origin. Now, I'm going to keep my eye out as I evaluate +1. Is that some kind of symmetry with -1? So that's 1 to the power of 3, which is 1 times 1 times 1. 1 times 1 is 1 times 1 is 1, 1. Now, I notice that the numbers are the same. The signs are not. So there's something different with this function than we saw with x to the power of 6. That's a 0.11. Can you predict what f at 2 will be based on the pattern we're seeing? So it's 2 to the power of 3, which is 2 times 2 times 2. All of those are positive, so 2 times 2 is 4. Times 2 is +8. Again, I see that the numbers are the same, whereas the signs are not. So as I write this, I need to think about how that's going to affect the symmetry of the graph. 2, 8. Let's graph those points. So I've got -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. Now again, to get from this framework to the actual graph, you might want to head over to Desmos and just type that function in. We'll do that for one of our further examples along. I kind of know the shape of this graph, but if you're wondering, okay, I got a framework, what's the graph look like? Go to Desmos, see the graph, and then come back to sketch your shape in. But I think we can catch this one pretty well. It ascends, does a little wrinkle, and then picks up its ascent. Now we got to ask ourselves about the symmetry. So here we've got the graph of the function. Does this graph show that reflectional symmetry like we saw in our last function if I folded it over the y-axis? Well, let's just think about this graph. If I were to fold this left or this right-hand side over the y-axis, it should be there, but it's not. So my initial feeling is that this is not an even function. So then I need to ask myself, if I were to rotate this graph 180 degrees, in fact, let me do it this way. I'm going to start at the y-axis. If I were to rotate this graph 180 degrees around the origin, would I get the same function? And my feeling is yes. This upper part of the graph would swing down and become this one, whereas this lower part of the graph would revolve around and become that upper part. So I'm going to make the claim, I think that this is an odd function. It shows that rotational symmetry about the origin. So then I need to go to the rule that is there for the odd function. So that's this one. And I want to calculate again f at -x and see, does that equal negative f at x? So we'll take those one step at a time. So I'm going to calculate f at -x first. So again, I'm just going to take the rule that we had, f at x equals x cubed, and I'm going to plug in -x inside the parentheses. So again, what we had done in the table will help us here in the algebraic proof. Let's expand that out. So that's literally -x times -x times -x. And again, I'll pair them so I can see what happens to the sign. -x times -x is positive x squared. Then I have that spare -x to the power of 1. And I put that power there so we can see what to do when we combine our powers. You add those powers together. So positive x squared times negative x to the first, the sign will be negative. And then x to the power of 2 plus 1 is 3. Now I need to compare that to negative f at x. So if it's odd, it should be the same as negative f at x. So what I'm going to do is I'm going to pull f at x. Again, we see it here in our original rule is x cubed. And then to get negative f at x, I'm just going to place a negative with that original function. Not a whole lot of work to do here. I just need to compare how does negative x cubed in the red compare to negative x cubed in the green. They're equal. So what we see is that we have the statement f at negative x for this x cubed equals negative f at x, which perfectly shows this odd symmetry from an algebraic point of view. So therefore it is odd. And again, just to say, what's my answer here? It is this algebraic statement. The graph and the table give us the tools to be able to make that algebraic statement. And that suffices as proof to say that this function is odd. All right, thank you for joining with these first two examples. We'll come back in a moment with two more examples about function symmetry, even, odd, or neither. Thank you for joining for this first section. See you soon.